Okay, so these are the expressions that we found when we used the boundary conditions with the general solution to Laplace's equation in spherical coordinates. And what we would do now is we would solve these equations simultaneously. So we would solve it for boundary condition 1 and boundary condition 2 for when L is not equal to 1. And we'd also do it for when L is equal to 1. Now, solving these expressions here simultaneously, what we'd find is that these boundary conditions can only be satisfied if AL is equal to BL is equal to 0, and that's for all of L. Okay, so now what we're left with are these relations on the right hand side. And what we do is we're going to solve this simultaneously. Now I'm not going to write it out in detail, I'm just going to give you the solution. So what you would obtain for A1 is equal to 3 minus 3 divided by epsilon r plus 2 by the electric field. And B1 would be equal to ER minus 1 ER plus 2 by R cubed E0. Okay, so let's go back to what a potential inside is going to look like. This would be in R theta. And what we're going to see is that for inside, when we have L is equal to 1, it will be equal to minus 3 by E0 divided by ER plus 2 by R cos theta. Okay. And this can be further expressed as minus 3 E0 divided by ER plus 2, and instead of R cos theta we can just write this as Z now, okay, by Z. Okay, so this is our potential inside the sphere. So what's quite interesting about this is if we now write out our electric field, what we find is that the electric field is going to be equal to 3 divided by ER plus 2 by E0. Okay, so in fact what we find is the electric field inside the sphere is uniform.